it is given that y equals to e to the power of arc sine x, and of course we are told that the x, okay, has got to be greater than -1 but less than 1, okay, and this is the given expression for y. So we need to show this differential equation. So let's look at how we can do that. So first step, I'm just going to copy down y is equals to e to the power of arc sine x as given, and if you can take ln to both sides, right? So if you take ln to y, so it will become ln y, and of course in order to get rid of the e, so I have taken ln, so log to base e would have become 1, right? So and the power arc sine x, you would have brought it to the front in front of the ln e, so therefore ln e is a 1, so 1 times arc sine x, so the 1 would have disappeared. So we simply get ln y is equals to arc sine of x. So now you can see that this is easy to differentiate, okay. So ln y, whatever that's after the ln becomes the denominator. So in order to differentiate this, we're going to differentiate the y and write it as its numerator, right? So y, if you differentiate with respect to x, it's going to become dy dx. So ln y differentiating with respect to x is going to give you dy dx over y. And on the right hand side we have arc sine of x. So if you differentiate the arc sine of x, okay, we can use the standard formula, which is 1 over 1 minus x squared square root, okay. So there we have differentiated the expression with respect to x. So now we have a y which we can cross multiply. So the right hand side is going to become simply y over square root of 1 minus x square. Let's make dy dx the subject. Dy dx is simply going to be y over root of 1 minus x square. So that's what we have. Now, but if you look at this, this is actually contains a second derivative, is a second order differential equation. So what we need to do is we need to differentiate it once more, but of course it would be easier to differentiate it implicitly because we are allowed to have a y, okay, not necessarily we need to express d2y dx square in terms of, you know, x completely. So what I am doing now is I'm going to cross multiply 1 minus x square to the left side. So I get square root of 1 minus x squared times a dy dx should be simply equals to just a y, right? And if I were to square every one of the terms, okay, 1 minus x squared square root, if I'm going to square it, okay, the square and the square root would cancel, just giving me 1 minus x square. And then dy dx, if I square it, it's going to become dy dx to the power of 2, and y, if I square it, it's going to become y square. So you can see we are getting somewhere closer to this, right? So it's got a 1 minus x square in a bracket, there's no square root sign at all, so it looks as somewhat similar. So in order to get to the second derivative, we need to differentiate it once more. So for the left side, I'm going to use product rule to do that. I'm going to keep my 1 minus x square fixed, and I'm going to differentiate dy dx to squared once. So differentiate again with respect to x. So I'm going to keep the 1 minus x square fixed, and let's differentiate this. So what will be the derivative of dy dx? Okay, so we will bring the 2 to the front. We're going to use the chain rule on this, and then subtract 1 from the power, and then we will differentiate the dy dx to write it down. So when you just differentiate it, 2 times dy dx to the power of 1, of course I don't need to write the 1, and let's differentiate dy dx, okay, because we are doing it implicitly. So dy dx, if I differentiate with respect to x, it's going to become d2y dx square. So we have kept this fixed and we have differentiated the dy dx square. So now I'm going to keep the dy dx square fixed and differentiate 1 minus x square. So let's keep the dy dx square fixed, and if you differentiate 1 minus x square, of course 1 you differentiate is going to become 0, minus x square, if you differentiate it would become minus 2x. So we're going to write minus 2x, and let's now go to the right hand side. Remember, we are differentiating with respect to x, so don't just simply write 2y, it is going to become 2y dy dx, because we need to differentiate y once again since we are differentiating with respect to x. So it will become 2y dy dx. Now if you look at what you have expanded, is there any common terms that we could just pull out and cancel from both sides? Here there is a dy dx, here there is a dy dx, but it's a square, so there is a couple of dy dx times dy dx, and here also we have got a dy dx. We could just factorize out and cancel out the dy dx. So it's simply going to become 2 dy dx, right? And then Okay, what I have done here is just to pull out the 2 as well as the dy dx, okay, outside the bracket. So since I have taken out 2 dy dx, so what I'm going to have here is 1 minus x square and the d2y dx square only, right? So from this I have pulled out the 2 and 1 of the dy dx, so the other x and the dy dx is going to be inside still, so it's going to be x times dy dx. So I factorize out from the left 2 and the dy dx. So if I go to the right hand side, I've got a 2y dy dx. So what are the numbers that I can cancel on the left and the right? Okay, as you can see, there's a 2 here, there's a 2 here, which I could cancel. There's a dy dx here, there's a dy dx here, which I also have cancelled. And therefore, what we have left is just what is inside the bracket here, 1 minus x square, d2y dx square minus x dy dx, and on the right hand side is equals to a y. So what can you notice? Okay, you can see that we just need to keep this on the left side, and we just need to throw minus x dy dx to the right hand side, and you would have actually proven that. So we just keep whatever this the second derivative and its coefficient on the left, and let's throw the minus x and dy dx to the right side. It's going to become positive x dy dx plus a y, and there we have it. We have already proven it, and if you did it this way, so you will get 4 marks. The part B says find the first 4 terms of the Maclaurin's expansion of e to the power of arc sin x. In order to find 4 terms of Maclaurin's expansion of e to the power of sin x, we already have y, first y, and then we have dy dx, that means the first derivative, and from this we actually have the second derivative, and we may need to go for a couple more derivatives in order to get to the 4 terms, right? So we have already shown this part. So let us look at the part B now. So I've got my y, I've got my dy dx, and I've got the expression which is in terms of the second derivative d2y dx square, so which all we can make use of to get the coefficients. Okay, so first, if you actually because you want the 4 terms, right? So 1 2 3 is what we have. Differentiate again with respect to x. So when we go to this expression, we can see that there is once more, there's a product rule. We're going to keep the 1 minus x square fixed and differentiate d2 y dx square. Once again, it's going to become d3y dx cube plus, of course, now I'm going to keep my d2y dx square fixed and differentiate 1 minus x square. It's going to give me minus 2x. And if you go to the right hand side, let's keep the x fixed and differentiate dy dx. It's going to become x times d2y dx square. And let's keep the dy dx fixed and differentiate the x. Of course, differentiating of a x is a 1. So dy dx multiply by just a 1. Plus, I've got a y here. Y, if you differentiate with respect to x, it's going to become dy dx. So if you look at this, we have got, okay, third derivative, second derivative, as well as the first derivative in this expression. So we could simplify them. There's a dy dx here, there's a dy dx, which I can combine it and write it as 2 dy dx. So 1 minus x square d cube y dx square. Okay, there is a minus 2x d2y dx square. Let's throw it over the right side. It's going to become positive 2x d2y dx square plus 1 more x d2y dx square. And how much is that going to become? Okay, 1 plus another 2 is altogether going to become 3x d2y dx square. I've got 1 dy dx and 1 more dy dx. That's going to turn it into twice of dy dx. So that is the simplest that we could bring this into. Now let's get ready to start evaluating the Maclaurin's expansion. So we need to find out what is the value of y0 when x turns to a 0. So the y0 would be, of course, I'm going to put the x as a 0. Arc sine of a 0 is, of course, going to become a 0, right? So it will be e to the power of 0. So arc sine of 0 is going to be 0. So it will be simply e to the power of 0. Anything to the power of 0 is equals to 1. That's right. So therefore, the first term y0, okay, is going to have a coefficient of 1. So y0 is a 1. Now let's go and evaluate what is going to be y prime 0. dy dx is also written as y prime. So I'm going to write it as y prime 0. Y prime 0 is going to be y0, which is of course 1, right? So we have already done it in the first step. So the numerator, I'm just going to replace it with a 1. And for the denominator, 1 minus 0 squared, of course, is going to become 1. And 1, if I square it, it's going to become 1 as well. So I'm going to have a situation of 1 divided by root of 1, which is ultimately going to reduce to a 1. y0 is of course a 1. So let's replace it. Over 0 square is 0, 1 minus 0 is a 1. So square root the 1 is going to be a 1. Therefore y prime 0 is also a 1. What about y double prime 0, okay, which is the second derivative value? So for this I can just substitute into this step itself, okay. X is actually a 0, so I'm just putting in the x as 0. So 1 minus 0 square is going to become 1 times y double prime 0 equals to the right hand side. X value is of course 0. 0 times anything is going to give you a 0. So therefore we don't even have to evaluate this. But what we have is plus y0. y0 is of course a 1. So it's going to become 0 times dy dx plus y0. And y0 of course you know is 1. So we are going to end up having, okay, 1 times y double prime 0 is simply y double prime 0. Y double prime 0 is equals to, okay, this part is going to become 0. So y0 is 1. So therefore y double prime 0 is simply a 1 as well. Now what about y triple prime 0? Okay, so we need to make use of this differential that we did just now. So once again, 1 minus 0 square y triple prime 0, which is on the left side, is equals to 3 times, we know the value of x is 0. So of course the second derivative's coefficient is going to become 0. So we don't need to bother about this. This would be a 0. So 3 times 0. And twice of this part is y prime 0, which is of course twice of 1. So it's going to be twice of y prime 0. Twice of y prime 0 is of course 2 times a 1. That will be a 2, right? So this part would become a 0. 1 times y triple prime 0 is simply going to become y triple prime 0. Y triple prime 0 is going to become 2 times 1, which is a 2. Therefore y triple prime 0 would become a 2. So we have actually gotten all the coefficients for, okay, the y prime, y double prime and y triple prime. So we have gotten all the values, and now we can just take the standard expression for Maclaurin's expansion and we can substitute all these values and evaluate them. Okay, so that's my y0, y prime 0, y triple prime double prime 0 and y triple prime 0. So by Maclaurin's expansion we know that y is equals to y0 plus y prime 0 x plus y double prime 0 x square over 2 factorial, y triple prime 0 over x cube over 3 factorial plus y4 0 over x4 over 4 factorial, and so on and so forth. It will keep going on and on, but I'm just stopping it at, you know, x cube term because the question only says give me the first 4 terms, right? 1 2 3 4 terms, so we can stop it at that. So what you're going to replace the y0 with? Of course it's a 1. So y is equals to y0 is a 1, so let's replace it with a 1, and y prime 0 is also a 1, so I have replaced the y prime 0 with a 1, but of course there's a x here, so let's write the x. Y double prime 0 is also a 1, so I'm going to just replace it with a 1, and x square over 2 factorial. What is 2 factorial? 1 times 2, that's a 2. So this is going to be x square over 2, and y triple prime 0 is a 2, so I'm going to replace the y triple prime 0 with a 2. X cube over 3 factorial is 1 times 2 times 3, that would be a 6, so it's going to become x cube over 6 plus dot 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 the rest of the terms. So now therefore y is equals to 1 times x is going to be simply x, and 1 times x square over 2 is going to be half x square or x square over 2, and 2 and the 6 we can simplify it to turn it into 1 and 3, right? So this term is going to become x cube over 3, and so on and so forth. So there we have expressed all the first 4 terms in the expansion of Maclaurin's expansion of e to the power of arc sin x. E to the power of arc sin x is simply equals to 1 plus x square over 2 plus x cube over 3, and so on and so forth. Okay, so that is the expansion, and if you did it right you will get another 5 marks for this question.